The name of our authoring tool is Instant Desert. It is a sand simulation implemented in C++ and Houdini. Here are a few clips showing results that were produced using the tool. The need for our tool stems from the ubiquity of sand and other granular materials on Earth and beyond it. Computer graphics artists whose work is to emulate the real world are more likely than not to someday encounter a need for depicting sand. Despite how simple it may seem, sand exhibits complex properties that make it notoriously difficult to model or simulate. It is, on the one hand, like a fluid in that it flows and assumes the shape of its container. At the same time, it is like a solid in that it can form piles and support weight. Capturing the way sand spreads across an environment and responds to collisions would require a large number of person hours if done manually. Therefore, there is a need for a tool that could automate such work. Instant Desert meets this need by simulating sand using a realistic physical model while giving the user high-level control over its behavior. Using a standard node-based workflow in Houdini, the user can specify one or more meshes or primitives that should form the base shape of the sand. They can do the same for one or more meshes or primitives that should be used by the simulation as collision objects. Finally, the user can adjust the physical properties of the sand using a set of parameters exposed in the user interface, or they can load a preset supplied by the system. Once everything is in place, the user can run the simulation and the system will generate OBJ files charting the movements of the sand throughout. These OBJ files can then be displayed by the plugin or used elsewhere. The algorithm follows a standard material point method pipeline, which uses particles and a regular background grid. Particles have mass, velocity, and position. Grid nodes have mass, velocity, and their own position. The material point method pipeline involves transferring the velocity and mass of particles to grid nodes and solving for each new velocity at the grid nodes with the influence of external and internal forces. The velocity is transferred back to the particles, which are then moved to their new positions. When a grid node is inside a collision object, either the velocity it stores is set to 0 if the user specified the stick behavior, or the normal portion of the velocity is set to 0 if the user specified the slip behavior. The piling and sliding behavior of sand is achieved by simulating plasticity and hardening. This is described in the paper Drucker-Prager Elastoplasticity for Sand Animation. In the paper and in our implementation, stress is divided into feasible and infeasible regions by a yield surface. Based on where the stress lies relative to that surface, the system can compute the plasticity force for the sand particles. Essentially, the system factors the sand's deformation gradient into elastic and plastic parts, with the elastic part containing the deformation that should be remembered and the plastic part containing the deformation that should be forgotten. In response to elastic deformation, the material will exert stress to restore itself to its previous shape, which accounts for the piling behavior of sand. The material does not exert stress in response to plastic deformation, which accounts for the sliding behavior of sand. These two behaviors work in combination to create a convincing physical model. After the plasticity and hardening step, the particle positions are saved, the time step is advanced, and the simulation of a new frame begins. The typical user workflow for Instant Desert starts with a user creating a geometry node. Then, within that geometry node, they add the Instant Desert plugin. It has two inputs, with the second one being optional. The first input needs a VDB that forms the base shape of the sand. The user puts down a mesh, applies a transform to place it where desired, and then converts it to a VDB using a VDB from Polygons node. Alternatively, the user can merge several meshes or primitives before converting them to a VDB. The second input works the same way. The user places meshes or primitives to be used as collision objects, converts them to a VDB, and connects that VDB to the Instant Desert plugin. Now the user has some options with respect to the simulation. They can specify how many frames should be simulated, how often they should be saved to OBJ files, and where those files should be stored. As for the physical parameters of the simulation, the user is given control over the bounciness, squishiness, and pileability of the sand, as well as gravity and an optional external force. For more technically inclined users, the time step and the cell size of the regular background grid are also exposed in the interface. Finally, the user can change the constitutive model of the simulation and specify how the simulation should handle collision. The plugin's defaults for these parameters are reasonable, and the user also has the option to load from presets or save their own. The console keeps the user informed as to the status of the simulation. Once it is complete, the user can select which frame the plugin should display in Houdini. This allows them to render the frames as a sequence using Houdini's renderer.